Hello students, very good afternoon to one and all. Good afternoon Anupriya, Divanankam, Janisha and Yebor, Manish, Nandini, Roshan, Sanjana, Tanuja and Pantoi. Have you all revised the thermodynamics lesson yesterday? Good afternoon Roshan, very good afternoon. So just let me know if I'm visible and audible to all of you or not. Can you all able to hear my voice? Yes? Am I audible to all of you? Good afternoon, Nandini. Good afternoon. Yeah, so I'm visible and audible to all of you, right? Fine. So today we are going to start with a new chapter. Okay, so how many lessons we have completed? Can anyone tell me the number of lessons we have completed so far in Enable Plus program? Can anyone tell me the number of lessons we have completed in Enable Plus program? How many lessons we have completed and what are those two lessons? Am I audible to you guys? Roshan, am I audible? Yes. Okay, we have completed two lessons. One is periodic table and the other one is thermodynamics. Okay. So today we are going to start with the third chapter of this Enable Plus program in chemistry, which is equilibrium. Okay, so are you all ready to go for the third new lesson today? So I hope all of you having your class notebook and pen, pencil with you. So try to follow the class from today onwards for this third lesson, okay? So entering into the lesson equilibrium. So before moving on to the exact concept of equilibrium, so let me take some examples, okay? So here I am having a container A, okay? Container A is filled with water. Okay, it is not fully filled, somewhat partially filled, okay, with water. Now I am going to have a container B. Now the container B is empty. Okay. So now if I have some connection between container A and B, what will happen? If I have some a connection between A and B, if the two containers are connected, what will happen? Can you tell me what will happen if the two containers are connected with each other? So the water will flow, right? Water starts flowing from container A to container B. Very good. Water flows from A to B. So, will it keep on flowing from A to B until the A gets empty? Will the water start flowing from A to B till the A gets empty or water? No, right? So water flow will stop at one point. Okay, water flow stops when the water levels becomes equal in both A to B. Okay, and we call this point as the equilibrium point. Okay, this process is called as equilibrium process for this two system. Okay, so now I am going to take one more situation. Okay, and this is the second situation. And in this situation, I have a floor and I have a block on this floor. Okay, a block is kept on the floor. And I'm going to give force. Okay, I'm going to give two force. One is called as FA and the other one is called as FB. Force A and force B. Okay, so one I'm going to give from one direction and the other one from the other direction. Now, if both the forces are equal to each other, that is, if FA is equal to FB, what will happen to this block? To which direction it will move? It will move towards left or it will move towards right, or there will be no displacement at all. What is the answer for this? Yeah, it will not move. So there is no displacement of block if both the forces are equal. Okay. Now what I can say? Now I can say that the system is in equilibrium with each other, and this equilibrium is called as mechanical equilibrium. This equilibrium is called as mechanical equilibrium. Yeah, the net force will be equal to 0, and so there is no displacement. Very good, Avinash. Very good, all of you. Now we'll take one more situation. Okay. So I have two objects. One is A and the other one is B. A is a hot object and B is a cold object. So what will happen if I keep these two objects together? Already they are kept closer to each other, right? So what will happen if I bring these two blocks together? The heat will transfer, right? So it will transfer from A to B. Yeah, very good. The heat will transfer from, no, it is not diffusion kind of thing. The heat will transfer from A to B. Okay. So it will keep on transferring the heat. A will keep on transferring the heat to B. Now you see the color. Almost both A and B have the same temperature. Okay. So the TA is equal to TB. So if the temperature becomes equal for both the blocks, so what will happen to the heat transfer? Will there be any heat transfer from A to B or B to A if the temperature of the both block becomes equal? No. Very good, Manish. So if the TA is equal to temperature of the object A is equal to the temperature of object B, there is no heat transfer. And we can say the system is in equilibrium, and this equilibrium is called as thermal equilibrium. Okay. So I have given few situations for equilibrium. Now I'm going to give one more last situation to understand the equilibrium. So here is that N2 plus 3H2 giving 2NH3. And the 2NH3 can go back to 3H2 and N2. Okay. So here you can see a symbol, and this symbol denotes the equilibrium symbol. Okay. And also that symbol denotes that the reaction is reversible reaction. Okay, it is a reversible reaction. Reactant can be converted to product and the product can be converted to reactant. Now, how much ammonia? Ammonia means NH3. Okay, this one. How much ammonia can be produced from above reaction at given condition? Can anyone tell me how much ammonia can be produced from above reaction at given condition? So though we have 2 moles of ammonia produced for this above reaction, and why 2 moles of ammonia is getting produced, and what is the concepts behind this? So those things we are going to discuss in this lesson. So when does the reaction go to the backward direction? And at what condition we will get the formation of this 2 moles of ammonia? So the answer to all these questions will be explained in this lesson called equilibrium. Okay. So firstly, this lesson has two parts. Okay. One is chemical equilibrium and the other one is ionic equilibrium. Okay. So this is the two half of this lesson. But before moving on to the chemical equilibrium, we have some small concept regarding the physical equilibrium. Okay. So we will study what is physical equilibrium, and then we will move on to the most important topic, chemical equilibrium. And after completing that, we will go on with ionic equilibrium. So I hope the gist of the entire lesson is clear to all of you, right? So let's go ahead with physical and chemical equilibrium. So under this topic, we are going to learn what is physical equilibrium, what is solubility, then introduction to chemical equilibrium, and one topic, law of chemical equilibrium and equilibrium constant under chemical equilibrium. Okay. So now let's go ahead with the first topic of this first main major topic called physical equilibrium. So what is physical equilibrium? Can anyone tell me? What are the three physical state of matter? What is the three physical state of matter? Solid, liquid, and gas, right? So these are the three states of matter. So one can be in equilibrium with the other. Okay, one state can be in equilibrium with the other. Very good, Mahalakshmi. Solid, liquid, and gas. So who will be equilibrium with each other? Who all will be equilibrium? First of all, solid can be in equilibrium with the liquid, and the liquid can be in equilibrium with the gas, and the solid can be in equilibrium with the gas. Okay, solid liquid equilibrium, liquid gas, and solid gas. All right. So I will give you one example under each case so that you can understand this better. Not a kind of example. It is a kind of understanding the concept using some uh, objects. Okay. So first, let me go ahead with solid liquid equilibrium. So now you are able to see a GIF, right? A picture on the screen. So what it is? What it is? Can you tell me what is this solid block that you are seeing on the picture? Very good. It is an ice cube, right? So the ice cube, what is the state of ice cube? Solid. And what is happening here? Solid is melting. Yeah, ice is melting. Ice cube is melting. So the H2O in solid form is getting converted to liquid form. And again, what is happening? The liquid is going back to the solid form. Now, this is called a solid liquid equilibrium. Okay. So, if the solid is getting converted to liquid, then we can say that the system is melting, and we call that temperature as a melting point. What is melting point? The rate of melting will be equal to the rate of freezing. Okay, so if they are equal, rate means speed. The speed of melting and the speed of freezing is equal, means then we can say that the solid is in equilibrium with the liquid. Got it? This is solid liquid equilibrium. Now let us go for the second type, liquid vapor equilibrium. So what is this? We have the water inside a container, and if you notice this very keenly, so some of the vapors are coming out from the container, right? Can you all able to see the vapors coming out from the water? Yes or no? Can you all able to see the vapors? Yeah. So what is this? So the liquid is getting converted to gas, and again the water vapor can be condensed to form the liquid. Okay. So when does the liquid will boil? At one particular temperature, right? So that point is called as boiling point. And if the rate of evaporation is equal to the rate of condensation, then we can say that it is an example for liquid vapor equilibrium. Okay. So now let me go for the third type, solid gas equilibrium. So this is the iodine chemical. It is in the solid form, and it is going to the gaseous form. So this is called as sublimation. This is called as sublimation. And again, if the gas is coming back to the solid state, then that is called as deposition. So all of you can able to see this, right? So it is going to the gaseous state, and again the gases, no, they are coming back to the solid state. So if the rate of sublimation is equal to rate of deposition, then it is solid gas equilibrium. Got it? So these are the three types of physical equilibrium. Got it? Any doubt from this? Shall we go for the general characteristics of this physical equilibrium? All of you can able to understand, right? Between solid, liquid and gas. Shall I go ahead with the next topic? Students, are you all awake? Yeah. Okay. So now let's go for the general characteristics of equilibria involving the physical process. So first of all, the physical equilibrium is possible only in a closed system at a given temperature. Okay? It is possible only in the closed system. You should not keep it open. Okay? It should be kept in the closed container. And both the process occur at the same rate. What is meant by both the process? If I am taking solid liquid equilibrium, then solid liquid. So that the forward reaction and the reverse reaction. Both the process should occur at a same rate and there is a dynamic equilibrium. Dynamic means moving, okay, from one thing to the other thing. So it should be, the equilibrium should be dynamic. It is not static. And the third characteristic is all measurable properties of the system remains constant. So what are those properties, measurable property? Vapor pressure, boiling point, freezing point, melting point, okay? So all those things, all the measurable property remains constant for that particular equilibrium. Okay, it will not change. For example, if I take the liquid gas equilibrium, the boiling point will not change. Okay, water boils at 100 degrees Celsius. So that 100 degrees Celsius is a constant. It will not change. Okay, so the measurable property, which is a boiling point, remain constant for that particular liquid gas system. Okay, so that is what they are trying to say here in the third point. So these are the three characteristics of the physical equilibrium. Any doubt from this? Shall we go for the second subtopic of physical and chemical equilibrium? Yes? Okay, I'll go ahead. The second topic is solubility. Okay, we should know what is solubility equilibria. So first of all, let me take solid in liquid system. Okay, solid in liquid system. And I'm going to take sugar in water as the example. I'm going to take a sugar which is a solid and I'm going to put inside the water which is a liquid and it will produce a sugar solution, right? So this is a water and that is a sugar particle. And if I mix the sugar in water, I will get a sugar solution. Okay. So if no more solid can be dissolved, if no more solid can be dissolved in that particular liquid which is a water, then we can say that the solution is a saturated solution. Okay. So I may have 1 liter of water. Okay, only 1 liter. And I can add only 50 grams of sugar into the 1 liter of water. Okay, only 50 gram of the sugar can be dissolved in 1 liter of water. If I try to add 100 gram of sugar to this 1 liter of water, do you think the remaining 50 gram will get dissolved in the water? Obviously, no. Okay. So the remaining 50 gram in that 100 gram of sugar will not get dissolved. Okay. Because no more solvent particles are available there to dissolve it. Okay. Such solutions are called as saturated solution. So for saturated solution, the rate of dissolution is equal to the rate of crystallization. So if I try to add more amount of solute, what will happen? They will form a crystal kind of thing. They will not form the solution. Okay, they will form a crystal kind of thing. So the sugar solution, if I try to heat it, it will form the sugar back again, okay, by forming the crystal and the water will get evaporated. So if this crystallization rate and the dissolution rate are equal, then we can say that the solution is a saturated solution and the solid is in equilibrium with the liquid. Okay. So now what is solubility? What is the definition for solubility first of all? Can you guys try the definition for solubility? Can anyone try the definition for solubility? Students, what is the definition for solubility? How can you define it? What is solubility? So I have got the answer from one student, Mahalakshmi, and she is saying that the soluble at all state which completely dissolve only 1 liter of the solution, Roshan. The amount of the solute can be dissolved in 1 liter. Only 1 liter? Okay. So let me go. Let me go with the definitions. All of your answers are partially correct. Okay. So very good for this try. Solubility is the maximum amount of solute dissolved in solution at saturated condition. Okay. So, or else I can say that the maximum amount of solute that can be dissolved in a specified amount of solvent. Okay, this is called as solubility. Now, I am going to give you some cases. Case number 1. If the amount dissolved is less than the solubility, okay, what I can do, I can still add more amount of the substance so that it can dissolve further. Okay. Such solutions are called as unsaturated solutions, and here more solute can be dissolved. And if they are equal, if the amount dissolved is equal to the solubility, then it is saturated solution. That's what we have discussed. And for the system, you cannot add more solute. Okay, no more solute can be dissolved. And the third case is if the amount is dissolved more than the solubility, then it is supersaturated solution. And in this case, the solute crystallizes and separated out from the solvent. Okay. So these are the 3 cases of this solubility. All right. So now the next is gas and liquid equilibria. So initially, first I have discussed solid and liquid. Now we have taken gas and liquid. So the gas I have taken is carbon dioxide and I want to dissolve this in water. So carbon dioxide gas is dissolved in water as you can see in the picture. Okay. So how will it get dissolved? So something is coming from above, right? What is that? That is the piston. That is the piston. So why do we use the piston? To give the pressure. We apply pressure using the piston. Okay, we apply pressure using the piston. So if the pressure is applied, just give me a second. Yeah. So if the pressure is applied on this gas, what will happen? The solubility will be more. Okay, and the solubility of gas and liquid will be more. And this solubility of gas and liquid depends on 2 things. One is temperature. If I increase the temperature of the system, what will happen to the solubility? Will it decrease or it will increase? Can anyone tell me what will happen if I increase the temperature? So this is the system. I have gas molecules, okay, inside the water. And if I try to increase the temperature of the system, what will happen? Will the solubility increase? No, it will decrease. Okay, why it will decrease? So on heating this, the gas particles will try to go far away from each other, right? So they will move here and there. They will be far away from each other. They will not be present inside the water. So in that case, solubility decreases with increase in the temperature. Okay. And the second factor in which the solubility depends is pressure. Now here in the picture you can see we are applying the pressure using the piston. What will happen? If I apply the pressure, all the gas molecules are coming closer to each other, and if they come closer to each other, they will get dissolved completely inside the water. Okay. So if the pressure is more, then the solubility increases. Very good, Mahalakshmi. Solubility increases with increase in pressure. Okay. So can you all able to understand this concept? So you will study this gas and liquid, solid and liquid examples, this concept in your 12th standard in solutions lesson. Okay, we have one chapter called solutions lesson, and that is the first lesson of your 12th standard, and you will study all these things in a detailed manner in your next year. Okay, don't have to worry. For now, you keep the points in your mind which I am teaching. Okay, so this will be very helpful for you for this equilibrium chapter. Equilibrium is also physical chemistry, okay, where it involves more number of formulas and concepts, etc., like thermodynamics. Okay, so going ahead, I am introducing a law called Henry's law based on this gas and liquid concept. So what is Henry's law? The mass of a gas dissolved in a given mass of a solvent at any temperature. So these are all the gases, and the mass of a gas dissolved in the given mass of the solvent at any temperature is proportional to the pressure of the gas above the solvent. So what they are trying to say, the mass is directly proportional to the pressure. Okay. So the mass is related with mole fraction, right? Mass is related with mole fraction. So what I can say, the pressure is directly proportional to the mole fraction of the gas and liquid. So the mole fraction is denoted by the letter X. Okay. Suppose in this container, if I have two particles A and B, to find out the fraction of only the particle A, I will find out the mole fraction of A. So mole fraction has one formula. So those things will be discussed in the later part. Okay, in your next year, you will get to know those things. Now for this particular period of time, just keep in your mind, Henry's law states that pressure is directly proportional to the mole fraction of the gas and liquid. Okay, if I remove the proportionality symbol, I have to introduce a constant, right? And that constant is called as KH. KH is called as Henry's constant. So P is equal to KH into mole fraction. Okay, X. And the unit of this KH, the Henry's constant has some unit. Okay, that is very important. The unit of KH is ATM, atmospheric pressure. Atmospheric pressure. Okay. So this is all about the Henry's law and the Henry's law equation. P is equal to KH into mole fraction. And the KH is inversely proportional solubility. All of you please take down this relation in your notebook. KH is inversely proportional to the solubility. If the KH value is more, then that particular gas will be least soluble in nature. Okay. So this is a concept about Henry's law. Now let me go ahead with one question based on this concept. Which of the following gas will have maximum solubility in water at standard temperature and pressure? STP means standard temperature and pressure. Okay. So here are the four gases and the KH value. So can you tell me which one will have the maximum solubility in water? Which one will have the maximum solubility in water? Just now I gave you one relation, right? KH inversely proportional to solubility. You can use this relation to find out the answer for this question. Very good. Very good, Ebor and Roshan. Helium, Anupriya, Rakshita, why carbon dioxide? See, the one which is having the very least KH value will be more soluble. So that is the meaning of inversely proportional relationship, right? Yes or no? What is meant by inversely proportional? Yeah, it is CH4. If the KH value is very less, then the solubility will be more. So in the question, they are asking us to find out the one which shows the maximum solubility. So for that, the one which is having the least KH value will be more soluble. So among the four values, the CH4 value is least soluble. I mean, the CH4 value is less, that will be more soluble. Okay. So the answer is CH4. Got it? So from Henry's law, mole fraction is equal to pressure divided by KH. And from this only we are getting the solubility is inversely proportional to the KH value. Since CH4 has the lowest value of KH, it is most soluble in water. Okay. So this is all about the physical equilibrium. I hope the physical equilibrium part, which is a very small part of this lesson, is clear to all of you guys. All of you can able to understand the three types of physical equilibrium and the solubility concept, right? Shall we go ahead with the chemical equilibrium, which is a very important topic of this lesson? Yes, good. So let's go to the introduction. Introduction to chemical equilibrium. Okay, equilibrium in chemical process. So if I want to study about the chemical equilibrium, I have to take a chemical reaction, right? So in all the chemical reaction, if you see, we will have some reactants and products. We may have one reactant and one product. We may have more than one also, right? So ultimately, we will have reactants and products. Now, if these two are in equilibrium with each other, then we call that as chemical equilibrium. Okay. So the first arrow which you can see, this one, okay, the arrow which is above, what does this denotes? This denotes that the reactant is getting converted to product. Okay. And the reaction is called as forward reaction. And the arrow which is below, in which the product is getting converted to reactant. So that is called as backward reaction. That is called as backward reaction. Now I am going to take one example. Okay. So the same example which we have seen in the beginning of this lesson. N2 plus 3H2 giving 2NH3. So here nitrogen and hydrogen are the reactants and ammonia is the product. Okay. So all of you see the picture. What is happening? The green color atoms are nitrogen and the pink color are hydrogen. So they are coming closer to each other and they are forming the ammonia molecule. And after the formation, what is happening? Again, the ammonia is going back to the nitrogen and hydrogen state, right? If the rate of the forward reaction is equal to the rate of the backward reaction, then we can say that the system is in chemical equilibrium. Okay. And coming to all the chemicals, we have to talk all those things in terms of concentration, right? So if they are equal in their rates, there is no change in the concentration. Concentration of both reactant and product will be equal and they are said to be in chemical equilibrium with each other. And chemical equilibrium is also dynamic in nature. Okay, it is also called as dynamic equilibrium because they are keeping on moving, right? N2 and H2, they are coming and they are doing some process and forming ammonia. And ammonia is again moving and forming N2 and H2. So it is in dynamic in nature. So it is called as dynamic equilibrium. Got it? Is it clear for all of you? If the reactant and product are in equilibrium with each other, then it is called as chemical equilibrium. Here the forward and backward reaction rate will be equal. Got it? So now let me show you a graph for both the process, for both, the forward reaction and the backward reaction. Okay. First, let me take the graph for forward reaction. So this is a graph for concentration versus time. Okay. So as time increases, as time increases. So you see here initially the time is t is equal to 0, and after 5 minutes, what is happening to the concentration? Initially the concentration is 20 mole per liter, and what is happening as time increases? The concentration decreases. And after 10 minutes, it is still decreasing. Okay. And after 15 minutes, it is again decreasing minutely. And after 20 minutes, it is following a straight line. Okay, it is not getting decreased, it is maintaining a single path. Okay, the concentration remains same after some time. And I can say this is that point. Okay, 15 minutes is that point. This is for forward reaction. Let me go for backward reaction. So backward reaction means the concentration initially will be 0. Okay. And after 5 minutes, the concentration increases. And you see it is keeping on increasing as time increases, and the concentration versus time, concentration of the product increases as the time increases. Okay, concentration of the reactant will decrease as time increase, and the concentration of the product will increase as the time increase. Okay, so these two can be plotted in a single graph, and the picture will look like this. So this is the green color line denotes the concentration of product, and yellow color line denotes the concentration of the reactant. So one decreases and the other one increases. And in both the cases, time is increasing. At one point, they are maintaining a constant value, and that point is called as equilibrium point for the reactant and product. Okay. So this is all about the graphical representation of the chemical equilibrium process. Now let's study the characteristics of this chemical equilibrium. So we have studied 3 points under physical equilibrium, right? So in the same way, we are going to discuss the characteristics of chemical equilibrium. Like physical equilibrium, chemical equilibrium is also possible only in closed system. Okay, you see here, system is closed. Okay, I have some reactants and some gas molecules are there, and it is attached to a piston. It is closed. The system is closed. And it is dynamic in nature, I already told you. And all the properties of system remains constant. So what are those properties? Temperature, pressure, color, concentration. All these properties remains constant. Okay. And the chemical equilibrium can be achieved from both the sides. Both means from left to right as well as from right to left. Okay. For example, H2 and I2 can form 2HI. In the same way, 2HI can be in equilibrium with H2 and I2. Okay, so this is the graph which shows this reaction. So it can be achieved from both the sides. Got it? So these are the 4 important characteristics of chemical equilibrium. So do you have any doubts till this? Do any of you have any doubts till this point? From the graphical representation and from the introduction and from the characteristics of chemical equilibrium? Is everything clear, students, for all of you? Shall I go ahead with the next topic? Dynamic means moving. Okay, it won't stay. As such, it will keep on moving from A to B and B to A, from reactant to product and from product to reactant. All right. Okay. Okay, dear students. Now let me go for the last subtopic of this first main topic, which is law of chemical equilibrium and equilibrium constant. To understand what is law of equilibrium, you need to know the law of mass action. Okay. So from law of mass action, I will take you to the law of chemical equilibrium. Okay. So to understand the law of mass action, I have to take a reaction, okay, in which the reactant and product are in equilibrium. For any reaction of this type, the rate of the reaction, for rate of any reaction is directly proportional to the active mass of the reactant. Rate means speed. What is meant by active mass? Active mass means the mass of the substance participating in a chemical reaction. Okay, the mass of the substance participating in a chemical reaction. So I have two substance, reactant and product. Okay, so those substance mass participating in that reaction is called as active mass. Okay, and that active mass is directly proportional to the rate. Okay, if the reactant mass is more, then the rate of the reaction is more. If it is less, then the rate of the reaction is less. So the substance can be anything. Okay, the substance can be anything. If the substance is a solution, if the substance is some solution, then the active mass, the term that you have to use here is molar concentration. For solution, you have to use the term molar concentration. And if the substance is a gas, then in that case, the concentration is represented in terms of partial pressure. Okay, the active mass is denoted by partial pressure. And if the substance is a pure solid, then in that case, it is going to be a constant. So it will be just the active mass will just be equal to 1. And also for pure liquid, it is a constant, active mass is equal to 1. So what are the two terms? We are going to use solution and gas. For solution, active mass is called as molar concentration, and for gases, active mass should be represented in terms of partial pressure. All right. So let me go ahead with this law of mass action concept. So the reaction is there. Rate of the reaction is proportional to active mass. Rate of the forward reaction is directly proportional to concentration of reactant. And if I remove this proportionality symbol, I have to introduce a constant, and that constant is called as Kf. Okay. So Rf is equal to Kf into R. Okay. Kf is the rate constant of forward reaction. In the same way, if I want to write the rate of backward reaction Rb, it will be proportional to the concentration of P. Because for backward reaction, the reactant is the product, right? So it is proportional to the concentration of P. So now if I remove this proportionality symbol, I will introduce a constant which is called as Kb. So Rb is equal to Kb into the concentration of P, where Kb is the rate constant of backward reaction. Okay. At equilibrium, what will happen? Both the rate of the forward reaction and the rate of the backward reaction will be equal, right? At equilibrium. So in that case, Rf has to be equal to Rb. Rf and Rb should be equal. So in place of Rf and Rb, substitute these values. So in place of Rf, put Kf into R, and in place of Rb, put Kb into P. Okay. Now you bring this Kb to the other side. It will go to the denominator, right? And bring this R, concentration of R, to the right hand side. That will go to the denominator, and both will give this step. Kf by Kb is equal to concentration of P by R, which is going to be equal to Keq. And this Keq is called as equilibrium constant. We have discussed this term in the thermodynamics lesson, right? Do you guys remember this? Keq. In the last formula also we have discussed, no, in delta G formula. Do you remember? Minus 2.303 into RT, logarithmic function of Keq. Do you remember that? Equilibrium constant formula which we have studied in thermodynamics lesson. I hope at least some of you remember that. Yes or no? So Keq is called as the equilibrium constant. It is equal to Kf by Kb. Okay. Now, if I take some other reaction, like AB plus AB giving C and D kind of reaction, what will be the formula for RF? It will be KF into the reactant. So we have two reactants, A and B, and also we have the stoichiometry coefficient. So that stoichiometry coefficient has to go to the power. Okay. So RF is equal to KF into AA into BB. Then for backward reaction, what will be the case? If I want to write RB, how I have to write? It is KB into concentration of C raised to the power C and concentration of D raised to the power D. This is RB, rate of backward reaction. Now, if I want to write KEQ, equilibrium constant, then it is KF by KB, right? It is nothing but KF by KB, which is equal to the corresponding terms. If you substitute, you will get this. And this is called as law of chemical equilibrium. Law of chemical equilibrium. So, for example, if I have N2 plus 3H2 giving 2NH3 reaction, I want to write the KEQ. What I have to do? I have to write the product concentration in the numerator. Who is the product here? NH3. So I have to write the concentration of NH3 raised to the stoichiometry coefficient 2 divided by reactants concentration. So I have two reactants, N2 and H2. Concentration of N2 into concentration of H2. H2 is having 3 as a stoichiometric coefficient, right? So put that in the power. This is how you have to write the KEQ, and this is called as the law of chemical equilibrium. Okay, which is very, very, very important. Very, very, very important. And also this KEQ has some unit. If you substitute the mole per liter in all the concentration term, so we have C, D, A, B, right? So in all the cases, if you substitute the concentration as mole per liter, unit of concentration is mole per liter. Unit of concentration is mole per liter. So in all the cases, if you substitute, you will arrive at mole per liter C plus D minus A plus B. Okay, this is the unit. This is the unit. So can you all able to understand? Can you all able to understand? Shall we solve one question? So I will give you some reactions. You guys try to find out the equilibrium constant KEQ for those reactions. Okay. So it will be a little bit difficult to type the answer in the chat box, but just give a try. Okay. You can unmute yourself and you can give me the answer. You can tell the answer by unmuting yourself. So here is the question. Write the expressions for KEQ for the following reaction. We have 4 reactions. The first reaction is 2NH3 giving N2 plus 3H2. What is KEQ? So it is a concentration of the product raised to the stoichiometric coefficient divided by the concentration of the reactant, right? So what will be the answer? N2H2 power 3 by NH3 2. Got it? So like this, find out for this reaction, second reaction, PCl5 giving PCl3 and Cl2. What is KEQ? Can anyone unmute yourself and give me the answer? Anybody is willing to unmute yourself and give the answer for this second reaction? Not even a single student wants to give a try by unmuting yourself. Roshan, can you try?
PCl3 into Cl2 by PCl5.
Yeah, yes, Nandini. Come on. Say it again.
PCl3 into PCl2 by PCl5.
Very good. The concentration of PCl3 into concentration of Cl2 divided by the concentration of PCl5. Very easy, right? So there is no stoichiometric coefficient for this reaction at all. So it is very easy. So for the third reaction, one of you try for this third reaction. Who wants to give a try for the third reaction?
Concentration of NO power 2 by
Okay.
concentration of
Concentration
into
of
O2.
into concentration of O2. Very good. Very good, Nandini. So other students, don't feel shy. Come on. Try for this last reaction. One of you try for this last reaction. Now Nandini should not try. Nandini should not try for this. Any other.
Concentration of CaO into concentration of CO2 divided by concentration of CaCO3.
Okay, now Roshan has got stuck here. You know why? So just see the Roshan might have tried for the second reaction or the third reaction, I can say, because in the last reaction, you see, we have two solid substance. What I told, for the pure solid, the active mass is taken as 1, right? It is constant. It is equal to 1. It is equal to 1. Okay. So the KEQ is equal to actually CaO concentration into CO2 concentration divided by CaCO3 concentration. Okay, this is correct only. But the active mass of the pure solid is equal to 0. You see here, calcium oxide and calcium carbonate are present in their solid form. So, those two will go to 1. Active mass will be equal to 1. So, I will be left only with the concentration of carbon dioxide. Roshan, is that all right? All of you, can you able to understand? If you're having a pure solid or a pure liquid, then in that case, you should not take the active mass of those substance. Clear? Roshan, your answer is correct only. But after substituting the value 1, we will get only the concentration of carbon dioxide. Clear? Is it clear? Yes. Very good, Roshan and Nandini. You both have come up, no? To give me the answer. That is great. So others also you can try. You can give a try and interact like this in the class. So KEQ will be equal to CO2 concentration. Okay. So this is how you have to find out the KEQ for different substances. I hope you have got at least some idea to solve some questions from the chemical equilibrium and the physical equilibrium. Okay. So today I will stop up to this. So we have studied what is physical equilibrium, what is solubility, and what is chemical equilibrium, and what is law of chemical equilibrium. Okay. So we have studied all these 4 topics today, and in the next session, we will continue this chapter with the types of equilibrium. Okay. So this is enough for today. And if you're having any doubt, you can ask me now. And if everything is clear, you can give me the feedback in the poll which I am launching, and you can get ready for your next class. Okay. So thank you so much for listening to today's lecture, students. Thank you so much. Go and revise. Please revise. Please revise the thermodynamics lesson and the equilibrium lesson also. Okay. Both of them are the 2 physical chemistry lessons. Main 2 physical chemistry lessons of class 11. So please give a try. So all of you give me your answer and then get ready for your next class. Thank you. Thank you, Mahalakshmi, Abhinash, Nandini. Thank you, all of you. Thank you, Tanuja. Bye. Take care.